Welcome to the second lecture of Unit 2. We have in the first lecture introduced linear time invariant systems, and we introduced the basic concepts of impulse response and step response of the system. Now it will become even more clear that what is the basic importance of linear time invariant systems are. First of all, we will consider the case of discrete time systems. And from the definition of impulse response, we shall start. So the impulse response of the system is the response of the system when we apply unit impulse signal at the input. So if, using that definition, I write, if I apply delta of n, I will get h of n. This is the definition. The impulse response of the system is the response of the system when we apply impulse signal at the input. Now we know that the system is time invariant, which means that if I present certain shift at the input, I will get that amount of shift at the output. So we will do that, and we will apply shift at the input. So delta of n minus k we apply at the input, and we measure the output, which due to time invariance shall become n minus k, because the system is time invariant. More than this, we also know that the system is linear, and linearity comes in two forms. First is scaling, second is superposition. Suppose we use scaling part, and I multiply x of k with the previous input, delta of n minus k, and apply that to the system. Due to scaling property, the output will also be the same scaled factor of the previous output. So here, if delta of n minus k was applied, h of n minus k was the output. If I multiply xk, due to scaling property of linearity, that output will also be multiplied by the same constant. We will now apply superposition. And superposition means that we shall apply summation of these. So superposition is not limited to two sums, it is limited to as many sums as possible, and therefore let us give k starting from minus infinity to plus infinity x of k delta of n minus k, and let us apply this at the input, and due to superposition property, the output will also be equal to sum of these individual terms. So sum means summation. So the output will also be summation of k starting from minus infinity to plus infinity, x of k h of n minus k. So from this we can go on and make our convolution sum definition. First of all, what is applied at the input? K starting from minus infinity to plus infinity, x of k delta of n minus k is what is applied. Similarly, at the output we get x of k summation starting from k equal to minus infinity to h of n minus k, and we get the same summation at the output. Now we will just investigate about the input. The input is xk multiplied by delta of n minus k. So we will use this, and therefore we can see that, just looking at what was the input, make it even more clear. If I look at the input is summation k starting from minus infinity to plus infinity, x of k h of n minus k, or rather it was not h of but delta of, right? It was delta of n minus k. If I look at this and I use the property of delta n, which is the impulse signal, delta of n minus k exists to be 1 when n is equal to k. It is not when it is not equal to k, not 0, k, right? So if this is the case, there is no summation here. It is basically, since the summation is in k, we will replace k with n. So I will have x of n. The input is x of n. So again, looking at our system, as the input is x of n, the output is k starting from minus infinity to plus infinity, summation xk into h of n minus k. This is my output y of n. This is my output y of n. Now this right hand side of the system, which is the output of the system, is what is called the convolution sum of the system. And therefore the convolution sum is defined as k summation in k starting from minus infinity to plus infinity, h of n minus k. Now as for the definitions that we have covered, all the three properties, time invariance, scaling and superposition, xn happens to be any input and yn is the corresponding output, which we can evaluate using convolution sum, for which we only require the characterization, that is h of n. H of n, we remember, is the impulse response of the system. If I have the impulse response of the system, I can evaluate the corresponding output of the system. Therefore, and this is why we study linear time invariant system, we can obtain output to a general input if we know the output of the system to an impulse signal. We can evaluate the output of any arbitrary input if we know the output of the system when unit impulse signal was applied, which is called the impulse response of the system. So if I have impulse response of the system, I can evaluate the output of an LTI system for any given input using what is called the convolution sum in discrete time domain. Remember, we are discussing xn, delta n, hn. We are discussing discrete time systems, LTI systems. This convolution operator is also represented with an asterisk sign. So this yn I shall again write because it forms the basis of the LTI system. Yn is basically equal to k starting from minus infinity to plus infinity xk h of n minus k. This is represented as, and this is again extremely important, as xn asterisk hn, which is called the convolution operator. This is called my convolution operator. So I can just calculate the convolution of the input signal with the impulse response. I can obtain any general response of the system, which is the output of the system. This applies only to linear time invariant systems, and of course we are talking in discrete time domain currently, and therefore I have considered the term sum and not the integral. So convolution is an operator. Discrete time it will be summation. You will understand from your till now understanding of the subject that in continuous time it shall become integration. Let us quickly apply what we have read. So suppose I have any arbitrary input xn, which happens to be equal to the impulse response of the system hn, which is a raised to the power n un. And if this input is applied to a system, the input is equal to the impulse response in this case, can I calculate what is the output of the system, which is, as I said, will be xn convolution hn. So can I evaluate the convolution of these two signals? We can apply the direct definition of this. So I can write y of n, which is x of n convolute with h of n. By the definition, it shall become summation k starting from minus infinity to plus infinity x of k h of n minus k. This is the definition of convolution. We cannot alter the definition. This is the definition of the convolution. Now let us put x of k and h of n minus k from what is provided to us. So that shall apply that y of n is equal to summation in k starts at minus infinity, goes till infinity. Now remember, xn is basically a raised to the power n un. So I can write x of k as replacing n with k. So I can write a raised to the power k u of k. Similarly, I can write h of n minus k, which will become a raised to the power n minus k u of n minus k. now we should consume, as we always do, these summations with definition of the unit step signal, and let us do that in just. So if I say that this is u of k, from our understanding we know that u of k is 1 for k greater than or equal to 0. It is 0 other than that. Similarly, u of n minus k, if you see, and remember the variable of summation is k, so I will look into it from k, not from n, from k. So what are the values of k that we need to appreciate here? So it will be equal to 1 when n minus k is greater than 0. So let me write that also. N minus k is greater than or equal to 0, which implies what? That n is greater than or equal to k. But I don't want about n, I want information about k. That is what I said. We will write that k is smaller than n, and therefore it becomes 0 when k becomes larger than n. And these two will now give me the limits of my summation. So now my y of n becomes, what are the limits? K can only be starting at 0, it cannot be negative. So the limit which was starting at minus infinity will now start at 0. K can be smaller than n, it cannot be larger than n, so it can only go up to n. And then whatever I had, so I had a of k. In place of u of k, you understand, I can put 1. In place of u of n minus k, I can put 1 similarly. So therefore what remains is a raised to the power n minus k, which I can write again to be extremely sure, k starting from 0 to n. Bases are same, powers are added, so it becomes a raised to the power n. And now we will just pay attention and see that n does not belong to the summation. So it is basically summation of 1 from k starting from 0 to n, and a raised to the power n is something which is not of k, so can be brought outside the definition, and therefore we can write this as a raised to the power n summation k starting from 0 to n of 1. Now from our previous concepts we know that the sum of 1 starting from k is equal to 0 to n is basically adding 1 n plus 1 times, because it starts at 0, so from 0 to n is there are n plus 1 points, and therefore this summation we know is n plus 1. So we can just put that in the summation and quickly evaluate what is our y of n. Y of n comes out, because a raised to the power n was there, it is getting multiplied by n plus 1. This is the output of the system when we applied the input a raised to the power n un, and we knew that the output of the system was a raised to the power n un when we applied delta n, which is called the impulse response of the system. Now, before coming to any conclusion, let us just quickly go back here and see what was happening in the summation, because that will actually give me an idea of what are the values of n that apply here, because that is also very important. The summation was in k, and we went on to see that there was this uk which was present, which makes it k starting from 0, and then there was this u of n minus k which made the highest limit to be n, and therefore we can see that while calculating the convolution there were no negative values of the signal that were considered. It is also very clear from what was given that the input is actually un multiplied by it, which means that it is a causal thing. And since it is a causal thing, it will most certainly be only right sided, and it will only produce a signal which is right sided. This information is not in the solution itself. This is from introspection. And from introspection, it becomes very important to make the output signal also causal. And therefore, I can just introduce a u of n with my output, and this yn is the output of the system when we were to apply an un to the system. If we knew that the impulse response also happened in this case to be an un, and therefore we can obtain the output of the linear time invariant system when we have the information about what is the input of the system by just evaluating the convolution sum in case of discrete time systems. The concept can be taken forward for defining convolution integral for a continuous time system. So I can just apply with the same concept. So I apply delta of t to the system, but the output I know is basically the impulse response of the system. Now with this strategy, I use the property of time invariance. The system is supposed to be linear time invariant system, and therefore will give me time invariance as property. So I will shift the input, suppose by an amount tau, and I apply that. I will get the output again shifted by the same amount. Next, I know the system is linear. The system is linear. If the system is linear, I can use again one more basic property which is called scaling. So I can just, with a constant term x of tau, I can multiply my delta of t minus tau and then apply. And the output which was coming before again will be multiplied by the same constant, given that it appropriately fulfills the condition of scaling. But linearity is not only about scaling, it also covers superposition. So I will apply superposition. In this case, you can understand the summation which was there earlier will become integral. So I can apply this integral from minus infinity to plus infinity x tau delta of t minus tau d tau. Remember, we are operating in tau, and this will give me an output which shall be, due to superposition, the same integral which was happening before. It will be integrated with respect to tau, and again with the same building upon which was in the last case. This left hand input, I can write the input again, which is minus infinity to plus infinity x tau delta of t minus tau d tau. This is nothing. This is just a particular value, because delta of t minus tau always exists only when t is equal to tau. Remember, we are operating in tau. So we'll replace tau with t in this integral, and that will be the value. So this is basically, this will become 1 at tau is equal to t, and we'll put tau is equal to t. So I will get x of t. So this gives me my system, which was linear time invariant system, that I apply input xt I measure the output yt, which comes out to be integral minus infinity to plus infinity x tau h of t minus tau. And again, very important observation, similar to the previous case, that we can obtain the output for any given input, which means that we have any arbitrary input, we can obtain the output if we know the information about the impulse response of the system. So this is my clear-cut observation. We can get the output to a general input if we know the output of the system to the impulse, and therefore I will now generalize this, that yt is equal to integral minus infinity to plus infinity x of tau h of t minus tau d tau, which is basically nothing else but convolution of the input to the impulse response of the system. In this case, since it's a continuous time system, this convolution is actually the convolution integral. In the last case, it was summation. So with this definition of convolution, we will build upon this and evaluate basic convolutions and see what are the various properties of convolution in the subsequent lectures. Thank you.